Okay, our next speaker is Akshay, who will continue in the same style of synthesis for Boolean functions. Thank you.
Thanks a lot. Thanks, Rujita and Moshe, for inviting me to this workshop. Yeah, and I think Kuldeep has already given a good prereqs on the problem statement and motivation for this talk. So I'll be talking on Boolean functional synthesis, but from a very different angle, or through the lens of knowledge compilation and knowledge representation. This is joint work with, all of it has been done with Supratik Chakrabarti, who's here in the audience, but also with Shetal Shah and Krishna from IIT Bombay, and a whole set of generations of undergraduate students who have worked on this and who are somewhere in Bay Area, many of them now, doing different things. Right, and let's get started. So again, I know that Kuldeep motivated all this very nicely, but there were some people I saw walking in after first 10 minutes. So let me just quickly restate the problem and go ahead. Remember that the problem is that we are given a Boolean formula with, let's say, m inputs and n outputs, and we want to automatically synthesize these Boolean functions, right, for each output yj in terms of all the inputs, such that this holds, right? For all inputs, it's the case that if there exists a way to make these the relation evaluate to true, then these column functions, when I plug in, should make it evaluate to true. And this is, of course, the column function for each variable in terms of the inputs. Yeah, so I think Kuldeep already explained the tractability when it comes to experiments. You can also see that theoretically this is a hard problem in a kind of a different way, which is to say that if you take a specification as this formula, right, which is just multiplication, x equal to y1 into y2, and you ask that y1, y2 are not 1. Okay, I'm looking at finite bit vectors, maybe written down as Boolean vectors. But now my input, I decide, is x, which is this formula, which is the product, and I want to output y1 and y2, right? So essentially, in this case, the Boolean functional synthesis problem asks to compute y1, y2 as functions of x, such that this relation is satisfied, right? Of course, this is a hard problem, because if you could obtain this, then you are doing finite bit factorization, right? It would break crypto systems. Let's also point out that you can also notice in this example that the specification doesn't always need to be satisfiable. There are, of course, prime numbers for which you will have no way to factor it to make the relation hold. But the question of Boolean synthesis still is valid, which is that whenever there exists an output, can we produce it, right? So this is really the question. Automatically synthesize the system, a function that satisfies the spec when that is possible. Is that fine? Are we all on the same page? Excellent. This slide I really will not cover. This was there because I like the slide. But I think Kuldeep covered pretty much a lot of this when he talked about the applications. I think one thing which maybe he didn't look at, and let's maybe start here, is how hard is Boolean functional synthesis? We saw that in practice it's really hard. We can see that the experiments do show the difficulty in scaling. But is there also a theoretical hardness? And in some work in 2018, we had shown that, this question was there last time also, which is that how is our specification and column functions? We are assuming that these are given as Boolean formulas. Further, they are given represented as negation normal formulae, right? So you take your favorite representation of NNF formulae as Boolean circuits, and your column functions are also required to be synthesized in the same form. It's obvious kind of to see that it's at least NP hard, but actually one can show much stronger results. One can show that unless the polynomial hierarchy collapses to the second level, there are specifications for which the column function that we synthesize must be super polynomial in the size of the specification. All right. And furthermore, if you are a believer in exponential time hypothesis, there is a non-uniform exponential time hypothesis whose falsification would be implied if you could get a sub-exponential time and size algorithm for solving this problem. Bottom line is that this problem, but non-uniform just means that There's no family of algorithms, one for each input size, which can solve 3-SAT in sub-exponential time. So under this hypothesis, we cannot expect for a better than, worst case, better than exponential time algorithms. So really the bottom line is that it's not only difficult in practice and building tools, but there are theoretical hardness sitting inside. Which brings me to the topic of this talk, is that are there specific properties that the specification given as an NNF formula can have, a structural property, let's say, or a semantic property, which will ensure that there is an efficient algorithm for synthesis, right? Of course, this is not always true, as the hardness results show. But then one could ask, if there is this was possible, whether one can compile into these forms, right? So if there exists such a form, that's the first question. And once there is such a form, can you compile into this? This is the second question, right? And this really leads us to this connection to this rich area in AI, which is this area of knowledge representations and knowledge compilation. And though there is no machine learning in this talk, I will try to relate it to this AI concept, if you wish, right? So that's really the kind of what I'm going to do in the remaining 20 minutes that I have. All right, let's take a quick inspiration from model counting. So if you take, so this is the formula written as a spec, and you have these outputs, inputs are there somewhere. And there is this normal form called a decomposable negation normal form, which for those of you who know, which basically says that no variable or its negation or a variable and its negation, no literal, should meet at an AND gate for the first time, right? And in fact, if you allow this and make one more assumption, which is a determinism assumption, this leads to polynomial time counting, model counting, right? Counting the number of satisfying assignments. And this is a very classical normal form in the AI literature and knowledge representation literature, and it has been used, and there are compilation tools existing for it, and so on. We take a slight generalization of this, where we say that let's define the a formula to be in weak decomposable negation normal form if it is only the case that no literal and its negation should meet at the at an AND gate for the first time. Okay, so this is of course much smaller or a weaker condition that we require, and surprisingly, it turns out that this form is sufficient to imply a polynomial time and size formula algorithm for Boolean functional synthesis. So the question really is why? What is this magic? What is the relation between such behavior as decomposability, and what is the relation between this and Boolean functional synthesis? So in the remaining maybe 5 to 7 minutes, I'll try to kind of give you an intuition of the high-level idea of this proof. Yeah. Let's start with something even simpler. Let's start with just one output. So if you had just one output, the specification is phi of xy, then it's very easy to see that actually phi of x1. Now, this is a formula which only depends on the input, right? This is a correct Skolem function for this particular output variable in the specification. Why is this? Well, I'll give you a one-line proof. Basically, a Skolem function means that you want to show that for any x, it must be the case that if there is a way to make it true, then plugging it in. We want to show that this function, when I plug it in, is exactly equivalent to this. But actually, if you see the left-hand side is nothing but phi of x1 or phi of x0, then you can see that if this equivalence just holds kind of elementarily, if the left-hand side evaluates to 1, then either this or this must evaluate to 1. If this evaluates to 1, then plugging it here, phi of x1 gives 1. The whole thing evaluates to 1, the right-hand side. And if this does not evaluate to 1, then this must be 0 and this must be 1. In that case, you will plug in, here will be 0, and the whole thing will be phi of x0, which evaluates to 1. So left-hand side always implies the right-hand side, and vice versa is also true, right? So basically what this means that this is the correct Skolem function, and the same kind of reasoning you can use to show that negation of phi of x0 is also a correct Skolem function. In fact, any interpolant between these two can be shown to be a correct Skolem function. This is what I think Kuldeep referred to in between in his talk as well. The question is, okay, one output is easy, but how do we lift this to multiple outputs, right? Is there a nice way under which we can lift this? And of course, there is one easy observation again one can make, which is that suppose you could do existential quantification till some point, right? Then basically all but one outputs, if you could do, if you can get the existential quantification of all but one outputs, then you have only one output, then I can apply this earlier approach, right? So all we need to do in some sense is to efficiently represent. So suppose I could have a representation of all but the output that I'm interested in, its existential quantification. So if I have a nice representation for that, then I could do the same game because I have only one output. Is that clear? So the question is, how do we get such a nice form? Well, there is already one thing that we know. I mean, what we need to do is existential quantification. So that's nothing but if I take the formula and if I plug in, this is the one cofactor for it, is plugging in 1 for y1 and 0 for negation y1. Similarly, we can take the 0 cofactor, and if I disjunct it, that's exactly a representation for this existential quantification, right? This is not surprising. And of course, this works, except that this results in doubling of the size of the circuit at each step. So if you have, so this is clearly exponential in the number of output variables that you have. So the question really is there a way to avoid this? Is there a way to get another representation which has these properties but does not double the size, right? And let's look at, maybe we'll start by trying to over approximate it, right? So the way we try to do, and here is kind of maybe the little bit of a tricky point, consider the same circuit, right, which we started with, the NNF circuit, except now, instead of each negation of an output variable, I replace all the negation by a new variable, right? So you have phi1 hat, phi2 hat, y1 hat, y2 hat, and so on, right? So in this case, because we are only looking at the first variable, I only replace the first one. All the rest are kept as they are. Is that fine? So now this guy is, as you can see, this NNF circuit is monotone in y1 and y1 hat, which is a new variable that I have introduced. Yeah. Now, in this, basically, I can now say what happens if I plug in 1 for y1 and 1 for y1 hat. In other words, I take phi hat is the circuit I call where I have made these replacements. I take phi hat, where y1, negation y1 has been replaced by y1 bar, everything else is the same, and I plug in y1 bar, y1 hat, both to be 1. Then how does this relate to these other two circuits? Well, it's easy to see that both of them actually imply this one. Why is that? Well, you can look at this. This circuit is monotone in y1 hat, right? So in negation y1 essentially. So that means that if there is any evaluation for which this circuit evaluates to 1, then by flipping the value of negation y1 from 0 to 1, you cannot make it evaluate to 0 because the circuit is monotone in that, right? So therefore, from here, this implies that. Similarly, on this side, because it's monotone in y1, if this side evaluates to 1, this must evaluate to 1. In other words, we have that the disjunction of both of these circuits must imply the positive form. This is just by which we call the positive form to evaluate to 1. So this side of the implication is always true. So in other words, this one, which avoids the doubling, is an over approximation always. The question therefore is, when is the reverse direction true? Because if the reverse direction is true, we have a nice candidate for us to be able to do the existential quantification easily. So what does it mean for the reverse direction to not hold? What it means is that we want this implication to not hold, which means for an implication to not hold means that this must evaluate to 1 and this must evaluate to 0, right? But what does it mean again? Let's go a little bit deeper. What does it mean for this to evaluate to 1? I'm just writing down the relevant variables and formula values here. So y1 hat, when I plug in 1, this phi hat must evaluate to 1. That's what we want. But I want this to evaluate to 0. But what is this? Remember that this is y1 hat. Negation y1 has been replaced by y1 hat. So essentially what we are saying is that if I have y1 to be 1 and y1 hat to be 0, then phi hat must evaluate to 0. Similarly, with 0, 1, it must evaluate to 0 as well. because of this side. So now what about 0, 0? Well, because of monotonicity, if both of these evaluate to 0, that must also evaluate to 0. In other words, the bad case, the case where this is actually an over approximation and is not equal to the existential quantification, happens exactly in this behavior, right? But what is this behavior? This is exactly an AND gate, is the truth table of a conjunction, right? So in other words, this does not hold exactly when for some value of the other variables, input variables, this y1 and y1 hat is exactly equivalent to phi hat. So this gives us actually a semantic forbidden condition. If we could ensure that this is not for every k, that for all yk hat, if this does not behave, the phi hat does not behave as a conjunction of yk and yk hat, then we can be guaranteed that we can always do this existential quantification without the potential doubling, and hence this gives us a condition for doing synthesis easily. Notice that this semantic condition is something which is co-NP complete. It requires a co-NP complete check. So one can ask, is there a syntactic condition? And now we can go back to our weak decomposable negation normal form. If you don't even allow me to meet syntactically at an AND gate, if you don't allow any output variable and its negation to syntactically meet at an AND gate, they cannot semantically behave as an AND gate, right? So therefore, this is clearly a sufficient condition for the having AND unrealizability, right? So this is something which we can generalize significantly more. So this is a syntactic form. We can generalize this to a semantic form as well, where we say, okay, you don't really need just this. You can actually make it a little bit better by plugging in, because if you can fix an order on the variables, right, then you can operate on them one by one. And when you're doing this operation, you can simplify the circuit by plugging in y1 hat to be 1 for all the variables before it, right? And this gives us, again, a better characterization. And this is what we called synthesis negation normal form. And the theorem really states that if your input specification is such that it's positive form, or it's happens to be in one of this, it is in decomposable negation normal form, it is in deterministic decomposable negation normal form, whatever, all of these, then we can have polynomial time and size Skolem function synthesis. What are these Skolem functions looking like? We now know, we can get an idea of what they should look like. They are actually very simple objects. They just take the positive form of it, which is obtained by taking the negations and plugging y hat to all of them, and plugging once in constants, once in 1, 0 for all the output variables, you get the positive normal. You get the Skolem functions. Does that make sense? So why is this interesting? This is also interesting because it turns out that SynNF is, in fact, super polynomially more succinct than weak decomposable negation normal form or DNNF. There are some conditions under which this holds, but pretty believable ones, which are themselves known to be exponentially more succinct than ROBDDs, right? At this point, I'm going to just tell you that we can also answer much more than this. In this case, we gave a sufficient condition, a semantic sufficient condition, but one can ask, is it possible to have a necessary and sufficient condition? And it turns out there is a very much more complicated definition, which I won't even go to, but there is a form called the subset and unrealizability normal form. And if you're interested, I would refer you to this Lick's paper from 21 on this, which allows us to give a necessary and sufficient condition for having polynomial time and size synthesis. All right. How much time do I have? 5 more minutes? We started late, right? Okay. So we could also ask not only the input, what if your output also should be in a nice normal form? Why? Maybe you want BDDs, right, as your input. Then maybe you want your output also to be in BDDs. And in that case, we have a characterization of how much the blow up will be. For instance, we can say that if it's an input first BDD, you can go within polynomial time. But if you have a BDD, we can go in polynomial time if you have the output representation as a SynNF, but we don't still exactly know what happens if you must have the output as a BDD. There is one question mark, but the rest is solved. Right, so that kind of brings me to the last 5 minutes of the talk, which is I would like to kind of tell you a bit more about the most recent advances that people are working on this. The first is, of course, that your input specification may not a priori be in this form. How do you then compile it to this form? In 2019, we had one algorithm, which is the one which was referred to in the previous talk as well. And there is another algorithm in Lex 21 paper. And the most recent one about this is last year, which is a more counterexample guided way to do this. I won't have time to go through any of this, unfortunately. But if you're interested, I'd be very happy to talk. We'd be very happy to talk after the. So bottom line is that there are many compilation algorithms. And the idea, like in model counting, like in other AI topics where knowledge representation is used often, is that if you come up with a normal form, don't worry, somebody will come up with a better compilation algorithm. And that's the hope here as well, right? The second question is, how do we, suppose we wanted not just any Scolem function, which is what all the tools till now did, but we want a specific Scolem function. Or if we want to represent the space of all the Scolem functions, is that possible? Is there a normal form which allows us to represent the space of all the Scolem functions? And it turns out that we can take, and this why would this be useful? Because if there is such a generalized normal form which allows all Scolem functions, you can use that and compile to that normal form, and then use, I don't know, your favorite logic optimizer to get the best Scolem function. One of the big problems in this area is that no matter which tool you take, whether it's Manthan or BFSS or C2Syn, we don't know a priori whether they'll give a small Scolem function. We don't have any guarantees about the Scolem function we get. And this could be one way to kind of approach this problem, which is to build a knowledge compilation for the space of all normal forms and then use an optimizer which will give you the best normal form by whatever the notion of best that you want to take up. Right? And in the CAV 23 paper, we have a proposal of what this should be. We define what is called the Scolem basis, and we explain how to build a counterexample guided algorithm to compile to this Scolem basis. Maybe if I have a couple of more minutes, I can tell you this and stop, or yes? Okay, excellent. Wrap up? Excellent. Right. So just to tell you that what do we mean by a basis? Basically, we just want to say that instead of compiling to one specification, we will compile to two in such a way that any Scolem function is an interpolant between these two. And this pair of functions will now be our basis in that sense. It's basis because it will be orthogonal and it will span all Scolem functions. So it's analogical to the basis in vector space. Right? And in fact, we can show that set of all Scolem functions for an output has a unique up to ordering Scolem basis. And so this is basically the idea. I will not tell you that actually for one output, again, it's very easy. And for multiple outputs, you can again do these knowledge compilation techniques to address this. I will skip all this where there is some work and kind of ideas about how to lift this beyond the Boolean case. But I just wanted to pitch this to say that even formulating the problem in that case, asking what a Scolem function should be is quite difficult. In some cases, people have looked at where it is only a term within the logic, but in general, you can ask whether it should be beyond a term in the logic. So this is some work which I think would lead to nice future work as we go on. Right, so that brings me essentially to my conclusion. Though, as we've seen in the last two talks, functional synthesis is a very fundamental problem with a variety of applications and techniques. Applying this lens of knowledge representation has allowed us to kind of, I think, understand some amount of the structure of the problem itself, right? Where our goal, hopefully, is to come up with a better or a more explainable way of synthesizing these Scolem functions. It is also promising in practice, as Kuldeep pointed out, using these machine learning techniques, and the Manthan tool scales up to 509 benchmarks out of 609. It turns out that more than half of them, actually, we can synthesize the entire Scolem basis for it, right? Not just one Scolem function. What about future directions? First is to actually use this with logic optimizer and build a tool which can do better column synthesis. This is still work in progress. We don't have the algorithms yet. The second is to build normal forms and knowledge representations going beyond the Boolean case. For instance, we already spoke about LRA. Do these normal forms work there? Right? This is a question which we do not have an idea, but we have nice hopes. And I'm happy to talk about that. And finally, this question of can we integrate this with reactive synthesis? I think Ruzitsa and Bernd wrote a very nice paper recently on can reactive synthesis and program synthesis ever be friends? And I think there is scope to write another one on can reactive synthesis and functional synthesis be ever friends? And that's where I will stop. Thanks.
Questions?
You didn't say how you handle unrealizable cases. Where does unrealizability falls out?
So in this case, we do not check for unrealizability. So we just say that our column functions are correct when it is realizable. When it's unrealizable, they produce junk. But you can check whether it is junk or not by plugging it back in.
But it doesn't tell you it's unrealizable. It just says that you generated a junk column function, right?
That is true. We do not build unrealizability check into the normal form, but we could talk about this. I think it would be interesting to integrate that as well into the normal form. Yeah.
I think I might have missed something. So when you measure the size of the thing, is it actually a circuit or a formula?
Circuit.
Circuit, right? Okay. Yeah. Got it. Thanks.
Talking about circuits, so let's then thank speaker once again.
Thank you.
And next talk will be exactly about the circuits, right?